Now this video is on eddy current inspection. Eddy current inspection works on the principle of determining the ease with which a material will accept induced current. An alternating current is induced into the material being tested. This AC is measured to determine the characteristic of the material. The ease with which a material will accept the induced eddy current is determined by four properties: its conductivity, its permeability, its mass, and by the presence of any voids or faults. The conductivity of a metal varies with its alloy type, grain size, degree of heat treatment, and its tensile strength. An eddy current test may be used to sort metals with regard to any of these characteristics. Electromagnetic analysis is a term which describes the broad spectrum of electronic test methods involving the intersection of magnetic fields and circulatory circuits. The most widely used technique in the eddy current. Eddy current are composed of free electrons which are made to drift through metal under the influence of an induced electromagnetic field. Eddy current is used in aircraft maintenance to inspect jet engine turbine, shaft, and vents, wing skins, wheels, bolt holes, and spark plug bores for cracks, heat, or frame damage. In aircraft manufacturing plants, eddy current is used to inspect casting, stampings, machine parts, forgings, and extrusions. Now the basic principle. When an alternating current is passed through a coil, it develops a magnetic field around the coil, which in turn induces a voltage of opposite polarity in the coil and opposes the flow of original current. If the coil is placed so that the magnetic field passes through an electrically conducting specimen, eddy currents will be induced into the specimen. The eddy current creates their own field, which varies the original field's opposition to the flow of original current. Thus, the specimen susceptibility to eddy currents determine the current flow through the coil. Now I am giving you figure for this to understand. The magnitude and phase of this counter field is dependent primarily upon the resistivity and permeability of the specimen under consideration, and it is the fact that enables us to make a qualitative determination of various physical properties of the test material. The interaction of the eddy current field with the original field results in a power change that can be measured by utilizing electronic circuitry similar to a Wheatstone bridge. The specimen is either placed in or placed through the field of an electromagnetic induction coil, and its effect on the impedance of the coil or on the voltage output of one or more test coil is observed. The process whereby electric fields are made to explore a test piece for various conditions involves the transmission of energy through the specimen, much like the transmission of X-rays, heat, or ultrasound. In the transmission of X-rays, heat, or ultrasound, the energy flow in beams having a recognizable direction and intensity obeys the law of absorption, reflection, diffraction, and diffusion. Receiver elements can be placed into the beams and direct measurement of energy flow is possible. However, in electromagnetic tests, the energy distributes itself in a vaguely known manner and undergoes a transformation in the process from magnetic to electric energy and subsequently back to magnetic energy. Since the induced currents flow in closed circuits, it is neither convenient nor generally possible to intercept them at the specimen boundaries. Furthermore, in eddy current inspection, a comparison probe is held on the material we are using as a standard and the test probe on the metal we are testing. The meter is balanced to a null indication when the test probe is on the reference material. When the probe is placed on the test material, the meter will indicate of null if the conductivity of the test material is different from that of the reference. The permeability of the material is a measure of its ability to accept lines of magnetic flux. If a bridge type eddy current tester is zeroed with the test probe on the reference material, it will indicate on off zero reading. When the test probe is placed on a material whose permeability is different from that of the reference. The meter in figure which I have shown earlier indirectly measures the current flowing in the probe, and the probe current is proportional to the current that is induced into the test specimen. The mass of the material being tested determines the ease with which eddy currents can flow. The probe is placed on the surface of the test material and is zeroed. And the meter will move off zero when the probe is moved over any part of the material whose mass is different. If the probe passes over an area whose opposite side has been eaten away with corrosion, the meter will indicate this decrease in mass by a deflection of the meter needle. The presence of any discontinuities or faults within the material will cause the meter to deflect. The meter is zeroed with the probe over sound material as the probe is moved over a surface free from faults. It will remain steady, but as soon as it passes over a crack or other fault, the needle will move, indicating its presence. Let me give this figure also because it is from the other text, which will give you more because it's written below it in detail. Number 1 is an absolute method of inspection. The bridge type eddy current equipment is used to measure the characteristic of a material by measuring the amount of probe current that flows when current is being induced into the test specimen. The meter is zeroed by balancing the bridge when the probe is held in contact with a sound piece of test material that is the same as the material being tested. When the probe is placed on the test specimen, it will cause an off zero meter reading if the characteristics of the test specimen differ from those of the reference material. Now number 2 is comparison method of inspection. This method uses a double coil probe, and instead of being zeroed with a standard piece of material, it indicates any difference in characteristics between the material under the reference probe and that under the test probe. The meter type eddy current instrument is very effective for the inspection of conductive materials and is well suited for field applications while being relatively simple to operate. It is limited in that only part of the output information is represented by the meter. Several eddy current instruments which use a two-dimensional display such as an XY oscilloscope are available and do not have the limitation associated with the meter type instrument. The two-dimensional display allows the operator to analyze all the output information from an eddy current test. An eddy current instrument using an XY display is shown in this figure. I am giving two more figures.